Wrestling with an AI image generator, trying super hard to get a character that looks consistently like them, but also doing something completely new. It's a tough balance.
Oh, absolutely. That tension, wanting that perfect character recall and total creative freedom, that's really what's pushing research in personalized image generation.
Right.
And today we're doing a deep dive into something called InstantCharacter. It's a newer framework that's making some pretty interesting progress on exactly that problem.
Okay, InstantCharacter. So our mission today is really to get under the hood, understand the core advancements it offers. We've got the research paper, some notes,
Hmm.
and we want to unpack its architecture, focusing especially on the innovative bits, the stuff that's genuinely new from, let's say, a more academic standpoint.
Exactly. It's not just what it does, but really digging into how it pulls it off and why that how is different and potentially better than what came before.
Perfect. So let's start there. What were the big headaches with the older methods that InstantCharacter is trying to fix?
Well, the paper breaks it down into sort of two main camps. First, you had learning-based approaches, often built on UNet architectures.
Okay.
These showed some promise, yeah, getting some character consistency, responding to text prompts, but they really hit a wall when trying to personalize open domain characters.
Meaning characters that are really diverse, unique styles, poses, identities.
Exactly. They struggled to generalize well. What they learned about one specific character didn't translate easily to another, very different one, and sometimes the image quality just wasn't quite there.
So they worked okay for standard stuff, but push them a bit and they'd start to wobble.
That's a good way to put it. Then the other camp, optimization-based methods, think Dream Booth maybe.
Right, I know Dream Booth.
These could actually customize those diverse characters pretty effectively, but the catch was you had to fine-tune the entire model, or a big chunk of it, for every single character.
Oh, wow. Okay, that sounds slow.
It was very time-consuming, and another big downside that fine-tuning often messed with the model's ability to follow the text prompt accurately for other parts of the image, like the background or the action.
So you gained character consistency, but lost some creative control.
Precisely. Plus, fast forward to today, we have these massive diffusion transformer models to DITs. Trying to do that kind of fine-tuning for every image generation, it just becomes computationally way too expensive. Almost impossible, really.
Yeah, the paper actually puts it quite starkly. For the UNet methods, it says, while these techniques achieve certain subject consistency and text controllability, they struggle to personalize open domain characters with diverse identities, poses, and styles. And for the optimization ones, dot tuning-based approaches require fine-tuning, leading to long customization time and limited text controllability. Moreover, inference time fine-tuning becomes computationally prohibitive for modern diffusion transformers with billions of parameters. Sounds like a dead end almost.
It was definitely a major bottleneck, and that really sets the stage for the shift towards these diffusion transformers, the DITs.
Okay.
The paper really emphasizes their advantages, more powerful generation, more flexibility, just greater capacity overall compared to the older UNets. Models like SD3, FLUX Bot 1, they're built on this tech.
So DITs are clearly a step up in raw image generation power, but using them for this specific tricky task of personalized characters. It's not just plug and play.
Not at all. The research makes it really clear you need a new way to feed that character-specific information into the DIT. You need robust adapter networks, ones designed specifically for DITs.
Adapters, like little add-on modules.
Sort of, yeah. They need to bridge the gap, ensure the character's unique features align properly with the massive knowledge stored inside these huge deity models.
And the paper mentions that just taking the old adapters, the ones that worked with UNets, and trying to use them with DITs, that doesn't work. Why not?
It comes down to scalability mostly. Those older adapters just weren't designed for the sheer scale and complexity of deities, especially the multi-billion parameter ones like FLUX. They couldn't effectively handle or integrate the character information within that much larger, different architecture. They essentially failed to scale up.
Got it. There's some good words here, too. On DITs. Modern diffusion transformers exhibit powerful generative priors and offer unparalleled flexibility and capacity.
Right.
But the challenge, fully unleashing their potential, requires a robust adapter network compatible with the framework.
The compatibility is key.
And the problem, we observe that directly applying traditional adapters to large-scale DIRDs often fails. These adapters cannot scale effectively. So a new approach was definitely needed for DIRDs.
Exactly right. And this is where InstantCharacter introduces its main innovation, what they call a scalable full transformer adapter. This is really the core technical novelty.
Okay, a scalable full transformer adapter. What's the significance there? What makes it scalable and why full transformer?
Well, the full transformer part means its internal structure is based on the same transformer architecture as the main DIoT model, which likely helps with compatibility and integration. The scalable aspect is crucial. It's designed so you can increase its depth, add our layers, and the size of its internal representations to match the complexity of the DIT it's working with.
Ah, okay, so it can grow with the main model.
Precisely. And it's not just one monolithic block. It actually has three main subcomponents, each playing a specific and quite innovative role.
All right, let's break those down. Component number one.
First up are the general vision encoders. Now, instead of just using something common like clip, they made a specific choice, SIGLIP.
SIGLIP, why that one?
The paper argued SIGLIP is better at capturing finer grained details, especially texture information. And for characters, getting those specific textures right, skin, hair, clothing, fabric, is obviously super important for identity.
Makes sense. Finer details for better likeness. What else?
The other innovative step here is they don't just use SIGLIP alone, they also bring in DynOff 2.
DynOff 2, what does that add?
DynOff 2 is known for learning very robust visual features. It helps make the character representation less sensitive to things like background clutter or slight changes in viewpoint, so it helps the adapter focus purely on the character.
Okay, so SIGLIP for detail, DynOff 2 for robustness.
Exactly. And then they combine the outputs from both using channel-wise concatenation, basically stacking the information together to get a really comprehensive starting point. The paper says this results in a more comprehensive representation of open domain characters.
That's clever, using two different encoders to cover more bases. Okay, what's the second component of the adapter?
The second part is the intermediate encoders. This section tackles a specific challenge. Those vision encoders, SIGLIP, DynOff 2, often work at a lower resolution than the final desired image.
Right, so you might lose detail.
Potentially, yes, especially fine-grained details needed for high-res output. So InstantCharacter uses a novel dual-stream feature fusion strategy here.
Dual stream, how does that work?
Okay, so Stream 1 pulls out low-level features directly from the shallow layers of SIGLIP and DynOff 2. Those early layers tend to capture more fine detail.
Okay.
Stream 2 does something different. It chops the original character image into patches, feed each patch through the encoders, and gets region-level features. So you have fine details from Stream 1 and broader region-specific info from Stream 2.
And then it combines these?
Yes, using dedicated transformer encoders for each stream and then concatenating them along the token dimension. It's a hierarchical way to integrate both the fine stuff and the big picture. The paper calls it hierarchical integration.
That sounds like a really sophisticated way to build up a rich character representation for high-res generation. Okay, what's the third and final piece?
The third component is the projection head, and they implement this using a time-step-aware Q-former.
Time-step-aware Q-former. That sounds complex. What's its job?
Its job is crucial. Take all those refined character features from the intermediate encoders and effectively project them into the DIT's denoising space. It's the bridge that translates the character info into a language the DIT understands during generation.
And time-step-aware, that relates to how diffusion models work, step by step.
Exactly. Diffusion models generate images by gradually removing noise over many time steps. Being time-step aware means this Q-former injects the character information differently depending on which stage of the denoising process the DIT is currently in.
So it guides the generation more precisely throughout the whole process.
Precisely. It allows for, as the paper puts it, faithful identity preservation while still enabling flexible adaptation to complex text-driven modifications. It interacts with the latent noise using attention mechanisms, making sure the character stays consistent but can still perform actions or change based on the text prompt. That dynamic interaction is really key.
Okay, wow. That adapter architecture sounds like a major leap. But the paper also stresses the training strategy is equally important and innovative.
Absolutely. They use a three-stage progressive training strategy. It's designed very deliberately to tackle different goals, consistency, text control, visual quality in sequence, using their big data set effectively at each step.
All right, stage one.
Stage 1 is unpaired low-resolution pre-training. They use character images without text prompts, just the images themselves, and train at a 512 by 512 resolution. The goal: purely learning character consistency. The model learns to reconstruct the input character image, forcing it to understand and preserve identity.
And why low res first?
Efficiency, they found, starting at 512 was, quoting here, significantly more efficient than 1024 for learning this core consistency, saving a lot of computational cost early on.
Smart. Build the foundation efficiently. What's stage two?
Stage 2 is paired low-resolution training, still at 512 resolution, but now they use paired data character images with text descriptions. The focus shifts to improving textual controllability.
So teaching it to follow instructions.
Exactly. Generating the character doing different things in different styles or scenes based on the text. The paper mentions this stage efficiently eliminates the copy-paste effect and enhances text controllability. It stops the model just pasting the character onto a background and makes it integrate naturally.
Okay, so first consistency, then text control, still efficiently at low res. What about the final stage?
Stage 3 is high-resolution joint fine-tuning. Now they move to high resolution and use both paired and unpaired data. The main goal here is boosting the final visual quality, the details, the textures.
Ah, the polish.
Right. They found that even just a limited number of high-resolution training iterations can substantially improve the visual quality and texture. So it leverages the text alignment learned earlier, but really pushes the fidelity using high-res data.
That whole three-stage process sounds very methodical, tackling one problem at the time. Quite an innovation in itself.
It really is, and none of this would work without the data. They curated a massive data set around 10 million images.
10 million.
Yeah. And crucially, it has that dual structure we talked about, unpaired images for stage 1, consistency, and paired text image sets for stages 2 and 3, text control and high-res tuning. Having that specific data set structure is fundamental to making the three-stage training work.
Right. The data enables the strategy. So how did it actually perform? What do the results show?
The paper shows strong results. Qualitatively, they argue InstantCharacter hits a better sweet spot, good image fidelity, strong character consistency, and it follows the text prompt well compared to other leading methods.
They compare it against quite a few, right? Mini control, easy control, ACE++, AUNO, even GPT-4o.
They do. They point out weaknesses in others, like mini control and easy control apparently fail to preserve character identity features sometimes. ACE++ reportedly struggles with complex actions.
And UNO.
Uno is interesting. They say it sometimes overly preserves consistency, which can actually make it harder to edit the actions or background using the text prompt. It's too rigid.
So InstantCharacter aims for that balance. Consistent, but still editable.
That seems to be the goal, yeah. And they show results comparable to the closed-source GPT-4o, which is pretty significant for an open approach.
That is impressive. What about stylization? Can it handle different art styles?
Yes, that's another strength they highlight. They show examples integrating style lores, like applying a Ghibli or Makoto Shinkai style. The claim is InstantCharacter does this well, keeping the character consistent and text editable while applying the style.
Better than others.
They specifically mentioned that Zhang and GPT-4o had more difficulty preserving styles flexibly without messing up the character consistency. The quote is pretty direct. It is difficult for Zhang and GPT-4o to preserve the styles flexibly.
Okay, so that combination of fidelity, control, and style flexibility really seems to be the key outcome here.
Absolutely. So wrap up the core ideas. InstantCharacter's big contributions seem to be that novel, scalable, full transformer adapter built for deities and that very deliberate three-stage training strategy. Together, using their large, structured dataset, they've pushed the boundaries on open domain character generation, aiming for that tricky balance of high fidelity and text control.
Yeah, it's a really solid example, especially if you, the listener, are keen on understanding the academic nuts and bolts of how AI image generation is evolving. These architectural and training innovations are where the real progress often happens.
For sure. And it points towards broader ideas in controllable AI generation, how we can better steer these incredibly powerful large models like deities towards specific nuanced tasks. It definitely opens doors for future research.
And for anyone who wants to really dig into the technical details, the code for InstantCharacter is actually open source. It's on GitHub. We'll make sure there's a link in the show notes if you want to explore it further.
It's pretty cool to see this kind of progress. Thinking about how these tools are evolving, it really makes you wonder what kind of creative control we'll have in the near future.
Definitely. Where does this lead next? How much finer-grained control can we achieve while still letting the AI handle the heavy lifting of generation? It's certainly an exciting space to watch.